Today we'll be doing the question 6 for the exam of chapters 13 to 14. We're going to be explaining about the simple pendulums and the physical pendulum. So for part A, it's saying that on an alien planet, a simple pendulum of a length of 0.600 meters has an oscillation at a frequency of 0.659 hertz. So we have to find the period of the pendulum. Now we know that the period is equal to 1 over the frequency. So this is very simple for us. All we have to do is just take our frequency that we have and just put it all under 1. So 0.659 hertz over the 1 period. We shall get what our period is. Check it here. 1 divided by 0.659. And this could give us 1.517, which we'll just round over to 1.52 seconds. So our period is equal to 1.52 seconds. Now for part B, what we're looking at is asking us, now we have to find the acceleration due to gravity on the planet's surface. So since we have our length, we have our period here, we'll be able to easily solve what is going to be our gravity. As we know, period is equal to 2 pi square root of length over gravity. So what we'll have to do is just move over. So we'll divide both sides by 2 pi. And we'll have t period 2 pi is equal to square root of L over G. We're going to square it on each side. So period squared over 4 pi squared is then equal to L over G. And then here we can multiply G on both sides to get it out. So now that G is on the other side, everything else, we have L. And then at this point, we can then multiply 4 pi to be on the same pi square. And then we also can divide the period t. So inevitably, we'll be left with gravity is equal to 4 pi squared times length all over the period squared. So now we'll just put all this in to the equation. 4 pi squared multiplied by our length, which was given to us, of 0.600 meters, divided by the period, which we got over here earlier, 1.52 seconds squared. So get this working here. 4 pi 0.600 over 52 squared. Then that will give us our answer of 3.26. Should be mess something up here because I did not square the pi. That is why. I was just missing that pi squared. Now we get the actual answer, which is 10.25, which can round over to 10.3. So gravity on this planet is 10.3 meters per second squared. As for the 0.6 meters, as oscillating between a period of 1.52 seconds, our gravity is then determined to be 10.3 meters per second. All right. So then we're going to move on to part C. Part C, it's going to be a different question now. It's going to be what must be the length of a single pendulum. This time we have to find the length if its oscillation frequency is to be equal to that of an air track lighter, a mass of 0.450 kilograms, attached to a spring force constant of 9.75 newtons per meter. So we are able to relate the angular frequency W, which is equal to the square root of spring force constant over the mass. So what we're going to do to relate these things together is solve for the angular frequency, which we're then going to input our numbers of 9.75 newtons per meter over our mass of 0.450 kilograms. And this is going to give us what the angular frequency will be. So square root 9.75 0.450. We get the answer. Then we have 4.65 radians per second. This would be result would be as if it was on a graph. We get an angle theta in the radians. So with that in mind, then what we're going to then use is how the angular frequency is equal to square root gravity divided by length. So what we'll first do is square each side because we want to solve for our length. And since our angular frequency can equal to the spring force constant over the mass squared, that means that we can also relate what we get here, which is our angular frequency, to how the angular frequency is also equal to the square root of gravity divided by length. Now to get that, we'll have to first rearrange these. We'll have to square each side. So now W squared equal to gravity over length. Multiply gravity on each side. Actually, multiply length on each side, my friend. And then we'll side. So that length W squared is equal to gravity. And then from here, we'll divide by angular frequency squared, both sides. So now our equation is going to be length is equal to gravity divided by angular frequency squared. So length is equal to gravity from 9.8 meters per second squared, what our normal gravity is, divided by, which we got right here, which is our angular frequency of 4.65 radians per second squared. So we'll solve for this here. 9.8 over 4.65 squared. Our answer for the length is then going to be 0.453. So yeah, so 0.453 meters, and that will be the length. So then we're going to move on to part D. Part D is asking, in a bicycle repair shop, a bicycle tire of mass M and radius R is suspended from a peg on the wall. The moment of inertia of the tire around the peg is 2mr squared. If the tire is displaced from equilibrium, so swinging back and forth, what will be its frequency of oscillation? So we have a tire around a peg that is on. Now, if let's say it was displaced in any way, moved in any way, it would then go back and forth in the oscillation. And we pretty much right now what's asking us is how to pretty much express this term in the variables that were given to us. So we know that inertia, I, is equal to 2mr squared. And we know that we're working with mass and radius. So we have a problem over here, or a equation, where we know that the frequency of something is equal to 1 over 2 pi gravity over inertia. Frequency is equal to this. Actually, I think it was angular frequency is equal to just the square root of gravity over inertia, but the frequency itself is that times 1 over 2 pi. So since we have this in mind, we know that gravity can also equal mass times radius, mass times gravity times, I think it was mass over size. I don't have the exact formula in front of me, but we do not have be gravity over inertia force. But either way, the equation goes the square root of mgd over inertia. And pretty much for inertia, we're going to be putting 2 mr squared over mgd. Now d is pretty much equal to r, as it's our radius, and it's our length. So we can then write this frequency is equal to 1 over 2 pi square root of mass, gravity, and radius over 2 mass, radius squared. So we can cancel out the mass, and we can cancel out an r on the top here. So our final equation is going to be 1 over 2 pi square root of gravity divided by 2 radius. And that would be the answer for part D. Now for part E, it's going to be asking us, let me flip page here. Part E is asking us that a rod has a length. Just do it somewhere in there in the middle. Part E is asking that a rod has a length 0.900 meters and a mass of 0.500 kilograms. Now, it's pivoted at what end? And the rod is not uniform. The center of mass of the rod is not at its center, but is 0.500 meters from the pivot. The period of the rod's motion, as a pendulum, is 1.9 or 1.39 seconds. So what is the moment of inertia of the rod around the pivot? So we have to figure out what is the inertia. Now we can write this as the equation that the period is equal to 2 pi square root of inertia over mass times gravity times distance. Now we have to solve for the inertia because it's asking us what is the moment of inertia. So we have to move this around and arrange it so that we have I as our what we're solving for. First thing divided by 2 pi and squaring both sides of the square root. So we get the 2 pi out, takes that out. Then we can square both sides. And we're left with period squared over 4 pi squared is equal to inertia over mass times gravity times distance. And we'll just multiply that both sides. So it would cancel it out. And inertia would then be equal to period squared multiplied by mass times gravity times distance all over 4 pi squared. That would be our equation. So since we have our values already here, we'll be able to input them. So it's going to be equal to our period, which is 1.39 seconds squared, multiplied by our mass of 0.500 kilograms, multiplied by gravity, which is 9.8 meters squared, multiplied by length 0.920 meters. All that will then be under 4 pi squared. So we're just going to input this right here in the calculator. We'll have 9 squared times mass of 0.50 times 8 times 0.900. Our answer would be you're doing is doing it inertia of the rod around the pivot. Center of mass is not 0.9, so we can't see the full length, but more so be 0.500 meters. So it would be around the inertia that we're looking for. And that, when rounded over, will be 0.12 kilograms per meter squared. And then that would be our answer for the inertia. That is all the parts. Thank you very much.